Well, in 1989, Ed Anders suggested that these interplanetary dust particles, which are typically 5 to 50 micron pieces from asteroids and comets, contributed an organic-rich layer of material to the primitive Earth, and that he suggested it might have been important for the origin of life on the planet. At that time, it was an interesting speculation because neither the types nor the abundances of organic matter in interplanetary dust particles had been measured. We've been trying for the last 15 years to characterize this organic matter using two types of high-sensitivity synchrotron-based spectroscopy. The problem is the whole particle weighs a nanogram and it's mostly rock, not organic. Recent modeling by Nezvorny and his co-workers suggests that about 85% of the interplanetary dust comes from short-period Jupiter family comets, and so I want to focus at least the first part of the talk on samples from Jupiter family comets like Wild 2 and Grigg-Skellerup. The samples I'm going to talk about are two different NASA collections in which they attempted to get material from specific identified short-period comets. The first was the Stardust collection, which I think everybody's familiar with, which was the 2004 collection of dust from the comet Wild 2 by impact collection into low-density silica aerogel cells. But the year before that, in 2003, NASA used a high-altitude research aircraft to try and collect dust from the Earth's stratosphere, coinciding with the Earth's predicted crossing of the dust stream of Grigg-Skellerup. And I want to talk about particles from both of these collections. The Wild 2 collection was a high-velocity collection, 6 kilometers per second. The particles left craters on aluminum foil and penetrated into aerogel and were collected in the aerogel. So we have two types of samples. Comparison of the crater and track sizes to laboratory shots suggests that the spacecraft brought back something like 0.3 of a milligram of comet dust. I'll just show you one of the organic results. This is a track. And what we did on this track was we started here and did infrared spectroscopy as we marched out further and further from the center of the track. The aerogel itself is contaminated with aliphatic CH3. It's part of the production process, and it's this peak here on the far left in the infrared spectrum. What you can see as we start at the center of the track is this aliphatic CH2 peak that gets weaker and weaker and weaker as we go up to 125 microns off of the track center. And if you look at a map of the CH2, the red region is its most concentrated, but you can see the CH2 goes out several track diameters. You can look at another track in the aerogel, approximately the same size, and it's only the CH3 contamination, so we're quite certain that it wasn't the impact of the particle that modified the CH3 and put CH2 there, because it isn't in this track. It was something indigenous to the comet, but it's something indigenous to the comet that vaporized. It hasn't maintained its physical association with the rocky material that's present along the track. And so we know there's some volatile organic compounds that we captured, and there are other groups that have measured other compounds that were captured in the Wild 2 collection. The problem with the Wild 2 collection is that we still have a lot of work to do on it because we need to shoot at 6 kilometers per second organic matter at aerogel and try and see how various types of organic matter are modified in the capture process. There's modeling that indicates that these particles experience, well, the shock wave in front of these particles reaches temperatures of several thousand degrees Kelvin. We know there's evidence in the tracks for the vaporization of iron sulfides. So we need to understand the high velocity capture before we can say much more about what the indigenous cometary organic matter was. And that's why I want to talk about this timed collection from Grigg-Skellerup. You know that intense meteor showers that you can see in the sky, one source can dominate over the background of sporadic meteors for a few hours or days. And in 2003, in a paper in Meteoritics, Scott Messenger from the Johnson Space Center identified 4 short-period comets that he indicated had the possibility of producing Earth-crossing dust streams that have low Earth encounter velocities. That's actually very important because low encounter velocities mean that the particles decelerate in the upper atmosphere. They don't have much energy to lose, and in the upper atmosphere we stop these particles in tens of kilometers as opposed to stopping them in a few millimeters as we did in the stardust collection. So the advantage of this is we heat the particles much less and we modify the organics much less. The downside of this is there is the sporadic background, so if you do a collection like this, you can't guarantee that all the particles in the collection come from the targeted source. But he suggested that NASA try and conduct one of these stratospheric collections, and it was conducted in 2003. This was his idea of how much dust was going to come from Griggs-Skellerup as a function of years across the bottom here, and this is 2003 when the collection was targeted. He also suggested that we could identify the particles that came from Griggs-Skellerup because the normal dust particles that come into the stratosphere have spent 20 to 200,000 years in space, and there are a number of things that happen to them during that time. For example, they accumulate solar wind noble gases like helium from the sun. There are damage tracks produced by heavy ions, and so he said that since this was fresh dust from Griggs-Skellerup, we should not see those effects in it, so these should look like extraterrestrial particles that are missing the long space exposure evidence. A number of groups have been studying these particles. I should add we have probably a billion times less this material than we have of the stardust material. We've got about 20 or 30 particles, each weighing a nanogram or so. But the groups that have studied them have found, indeed, that many of the particles have low abundances of solar wind helium, high abundances of free solar silicates, and even a new mineral in an IDP that was devoid of solar flare tracks. That's another indication of short exposure. And so the people who've studied these particles in detail say all of the results are consistent with there having been a majority of the particles in the collection having come from the targeted comet. We've done some chemistry on these particles and found that about half of the 8 that we looked at have a chemistry consistent with chondritic meteorites, which would plot on this line up here marked 1. This is 4 of the particles that are scattering around the line. The other 4 are very different from chondritic. And we did some X-ray diffraction to try and understand the mineralogy as well. We've now done measurements of the organic matter by infrared spectroscopy in 4 of these particles, and I want to look at those 4 now. The first particle that we looked at, this particle called D1, has only the signature of the silicone oil in which the Johnson Space Center collected it. That's the CH3 feature of silicone oil. And nothing else, and so this particle just has the silicone oil contamination on it. We intentionally didn't wash these particles. Normally they're washed to get the silicone oil off. We intentionally didn't do that in this case because we were interested in seeing if maybe there's organics that are being washed away during the silicone oil, during the wash with hexanes to get rid of the silicone oil. So I'll look at the other 3 particles now. D4 gave a very low count rate in the X-ray microscope, which is consistent with it having a lot of elements lighter than sulfur, maybe organics, but it has a nickel-iron ratio that's chondritic, which indicates it's an extraterrestrial particle. Our infrared observation confirmed our X-ray diffraction analysis that said that this particle was dominated by a silicate pyroxene, and its spectrum is the green spectrum here. You can see it's dominated by CH2, not the CH3 from silicone oil, and its CH3 peak is shifted from the silicone oil peak. So this is presumably indigenous organic matter in the particle. What's really interesting about this is when we see this in normal IDPs, we see a couple of percent at most of this CH2 relative to the silicate, and what we see here is more like 10%. This particular particle is 4 or 5 times as rich in organic matter as the normal IDPs that we've been looking at. We have another example of a particle like this. It's shown by the purple spectrum up here. It's almost identical to the other one I showed you, except this particle is dominated by chromium and titanium, not iron. It's not dominated by a silicate mineral. So if this is also a cometary particle, it has a very different mineralogy, and that's consistent with what we saw at stardust. We saw particles this big that were dominated by things like the mineral chromite, which would be the chromium phase. And I'll show you one more particle from this set, E4. E4 has, again, a different spectrum. It's this blue spectrum, again dominated by CH2 and looking nothing like the CH3, but shifted in both its CH2 and CH3 positions from the other particles. And so it's quite different in its organic bonding. I want to talk a little bit about particles we don't know the origin of. These are the normal chondritic porous interplanetary dust particles, because we found something interesting in these in the last couple of years. Based on the degree of heating on atmospheric entry, Brownlee in 1993 suggested that these are cometary particles. A typical particle consists of, 10-micron particle consists of about 10 to the 4th anhydrous grains. And the individual grains have all been known for some years to be coated with carbon. We wanted to look at that carbon in more detail, and so we used a scanning transmission X-ray microscope, which I'm not going to have time to explain in any detail, but we can use this to map the distribution of carbon in these particles, and we found something remarkably interesting. The gray things are the individual mineral grains, the light gray is just the substrate they're sitting on, and all that red is organic matter that's characterized by a carbon-Zane spectrum, which measures very much the same sort of thing that infrared spectroscopy does, measures the transitions in functional groups. It's dominated by C double bond C and C double bond O. This is not elemental carbon, it's organic carbon, and it's quite rich in this organic component. But the question is then, where did it form and how did it form? And we got very lucky in one case. We had a small bit of this material that pushed away from the edge of the grain here. It's this little tail here. And we were able to do both carbon, nitrogen, and oxygen Zanes measurements, which gives us the abundances of all three elements. And we determined a C to N to O ratio of 110 to 50. Which is much higher than the ratio that you see in the insoluble organic matter in meteorites that you're going to hear about in a few minutes. And George Cody, about the time we were doing these measurements, was doing measurements of how the O to C and N to C ratio correlated with the degree of thermal metamorphism of meteorites. He found that the most thermally metamorphosed meteorites have low O to C and N to C, and as you decrease the thermal metamorphism, they go up along this trend line. Our particle actually plots up here somewhere, right about in that position on the extension of the trend line, and suggests that this material is significantly less thermally processed than the organic matter in the most unmetamorphosed meteorite. How did this material originate? Well, if you look carefully at this picture, you can see that we have grains of material. These are probably the first grains that formed in the solar system that are now coated with organic contact surface between the different grains. And so the logical way to explain this formation is a three-step process, that the grains formed from the solar nebula. They were coated by organics before the first dust grains assembled, because the dust grain, the whole big thing, is this assembly which is held together by this organic matter that's coating the grains. These can't be primitive interstellar grains, because those would be mostly non-crystalline, and most of these grains are crystalline. So they're probably solar system condensates that were then coated in our solar system with organic matter. And so we started thinking about how this organic matter could have formed, because this is always one of the burning questions. It's inconsistent with any sort of catalysis process that's mineral specific, because all the different minerals in the particle are coated with this organic matter. And it's very consistent with the mechanism the Ames group and other groups have been proposing for some time of the condensation of carbon-bearing ices that are then altered by UV or ionizing radiation. And if that's right, then what we have here is a sample of the earliest, probably the earliest solar system organic matter that formed by this ice condensation mechanism. And this is the volatile remains after the gaseous phases were given off as the grains subsequently heated. We're currently trying to do infrared spectroscopy on this material. Of course, the problem is they're 100 nanometer thick rims. That's well beyond the range of infrared spectroscopy unless you use the new techniques of near-field infrared spectroscopy. And so we're hoping to get some spectra on these at some point in the near future. And I'll stop there.